Okay, so we are recording now, and we're looking at torque converters. When we're talking about torque converters, we already reviewed the basic components inside the torque converter itself. On the picture we have here, which is the same picture that you got in your workbook, there is one piece missing, and that's the torque converter clutch. All right, the torque converter clutch, like I said, goes in between the housing, the torque converter housing, and the engine side and the turbine. Okay, so the clutch itself goes to the, we're calling it the turbine shaft in this picture, but realistically that's the transmission input shaft. Okay, the transmission input shaft is what the turbine drives. And when we're in the lockup phase, or this coupling phase where we get to this 1-to-1 efficiency, the only reason we're actually 1-to-1 is because of the torque converter clutch. If we didn't have a torque converter clutch, there'd always be a little bit of slip there. The different phases of the torque converter operation are the sort of torque amplification and then the coupling. And torque amplification happens, like I was saying earlier, when we have vortex flow, which is like this. And vortex flow means, yes, of course, the entire torque converter is turning, but the oil is being slung from the impeller because of centrifugal force, and it hits the turbine, and it causes the turbine to want to turn in the same direction as the impeller is turning. As that oil comes back out the bottom, it hits the stator. And you have to realize that if the impeller is turning faster than the turbine, that means there's going to be a difference in speed as the oil exits the turbine and tries to enter the impeller. That difference in speed means that there'd be a lot of turbulence in that transition portion there. Turbulence that's not beneficial to the operation of the torque converter, let's put it that way. So how do we get around that? Well, we put the stator in there, and the stator is basically just a vane, and it redirects the oil flow. So when the oil exits the turbine, it hits the stator, kind of makes effectively a little bit of a U-turn there. And that helps the oil hit the backside of the impeller, if you want to think of it that way, or the inside portion of the impeller. It helps it to hit that without causing a great amount of disruption in terms of, speed change and turbulence there. Okay, now that all makes sense and that all works great right up until the point that we're in this coupling phase. When we're in the coupling phase, the amount of speed difference between the turbine and the impeller here is very little. They're both turning at roughly the same speed, or as close as they're going to get anyways, because there's always some slip in a fluid coupler. Well, that means that if I still had the stator fixed in place, there would be a huge amount of turbulence over here now. So in order to make sure that doesn't happen, we have this overrunning clutch. The overrunning clutch allows the stator to freewheel when we're in that coupling phase and when we're in that rotary flow phase. And when we're in the rotary flow phase, all of the oil in the torque converter, if this is the torque converter itself, all of the oil is flowing like this instead of like this. Make sense? So in terms of torque converters in the ag industry, do we have these? Do we use these? Well, obviously not quite as common in the ag industry as it would be in the heavy industry, but you're still going to see them when you got, say, automatic transmissions in your floater trucks, things like that, right? Very relevant in terms of automatic transmissions in all of the automotive stuff that you'd see. And in the truck transport side, we're starting to move away from standard transmissions more in favor of automatic transmissions. I think that that's just one of those things where it's just easier to drive an automatic, and the skill level that it takes might not be quite the same as, say, for a standard transmission. So it's a little easier to get somebody in the seat and start holding that steering wheel, right? So in terms of where we're going to see these, they're in the industry across the board, all right? The next thing that we should talk about a little bit here is what we would have behind this this torque converter. And the torque converter is going to be driving an automatic transmission. What do you have inside of an automatic transmission? You've got some wet clutches, some brakes. We call it a brake when we're actually holding something to the case, right, and stopping it, or a clutch when we're joining two things together to make them rotate together. And probably some planetary gear sets. So for our planetary gear sets, we can start with a simple diagram showing us what a planetary gear set actually does. Okay, so a planetary gear set has got three major components, doesn't it? Now those three major components, the big one on the outside is the ring gear. The next thing that we have is the carrier, and the carrier is the part that has, the actual pinion gears in it. And then if we take a look at the middle, then we have the sun gear. And if you think back to what you would have talked about in previous levels of apprenticeship for the operation of a planetary gear set, then you'd probably understand that depending on which one of these is the input, which one is the output, and which one is held, we can create either forward or reverse various different underdrive and overdrive situations. Planetary gears are very useful because they're very versatile. So if you get a planetary gear set, of all of the gears that I've shown you here, the one that's effectively the smallest in terms of ratios would be the sun. And the next one would be the ring gear. And the largest would be the carrier. Now, how do I figure out what the effective tooth count of the carrier is? Do I just go ahead and count all the teeth on the planet pinions? No. I have to add together the sun and the ring. Let's just go ahead and throw some numbers up here. 10, let's say 30, and then for the carrier, well, let's go ahead and call that one 40. Just assuming that we have to assign some numbers so that we can talk about how we'd figure our ratios here. Okay. The next thing that we have to understand is if we apply the ratio math of driven over drive, then it's going to depend on what's our input and what's our output. If you got a small gear driving a big gear, that's going to give us an underdrive. If I got a big gear driving a small gear, that's going to give us an overdrive. Okay. Now, how do I get reverse out of this? I have to hold the carrier stationary. And that means that if the ring gear is turning in one direction, the planet pinions on the carrier act like reverse idlers, right? And then that's going to cause the sun gear to turn in the opposite direction of the ring gear. How do I get direct drive? The way I get direct drive is by holding two components.
So there is actually 7 range in the plane.
Technically, there is the possibility to have 7 different ranges in terms of speed and direction options out of a single planetary carrier. We usually don't do that because the ratios are a little impractical. So sometimes what we'll do is we'll have maybe a compound planetary, right? So we have one planetary driving another planetary, and maybe we'll grab, some of the speeds out of the first one, some of the speeds out of the second one. Sometimes we'll do a double reduction through both of them. There's lots of options when it comes to planetaries.
So some places they're talking about 6 and some other places are talking about 7, but I guess
If you count direct drive, that's where your 7th is. Yeah. Okay. And yeah, in terms of there being 7 different ratios, yeah, there is 7. And the 7th would be direct. And if you're not counting direct, you just calculated ratios, then yeah, there's 6 of them. All right. All of this, planetary information here, it applies in terms of power shifts and automatic transmissions. It also applies to the final drives, the gear reduction in the final drive. And it's really, really normal to have a big planetary gear set as our final drive. And one of the interesting things about planetary gears as the final drives is, depending on how we set that up, we might actually be able to use that for what we could call differential steering. What kind of a tractor would need differential steering?
the 2-track tractor.
You got a track type tractor, and yes, 2 tracks. Thanks for pointing that out, because a quad track does not need this. It doesn't matter if your quad track is painted red or blue or green. Those are articulated steering units. They do not rely on differential steering in order to go around the corner. But if you've got a 2-track, which is probably painted either green or yellow, then those ones, they need to have a way to speed up one track and slow down another, and they're not hydrostatically driven. Okay. The simplest way to explain what they do with those is they take a planetary gear as a final drive on both sides. That planetary gear set is going to be driven by a crown and pinion gear set, which is driven by the transmission. That crown and pinion gear set does not have a differential in it. So it's interesting that we call it a differential steering system. All right, but that's not actually, it's not actually a differential in there. It's just a solid drive to both sides. That solid drive to both sides is going to power the sun gear. Okay. The sun gear is going to power the planet pinions, which are connected to their carrier, which is connected to the axle, which is connected to the tracks. If I want to speed up one side and slow down another, that means that, and as I have it drawn here, if those were just normal planetary final drives, it would only ever drive straight. So how do I get this thing to go around the corner? It's surprisingly simple. I take a hydraulic motor, a steering motor, okay? And that motor is going to be connected to what's effectively a little set of gears here. And then one side is, I'm just drastically simplifying what actually happens here. But basically, if this hydraulic motor was able to turn this shaft, all right? And if that shaft was coupled to the ring gears, if the outside of the ring gears actually had gear teeth on them instead of being just part of the trumpet housing, that would mean I could take that ring gear and I could speed it up or slow it down by taking the steering motor and speeding it up or slowing it down. I could take this hydraulic motor here, and if I just locked it in place, neither one of those ring gears would turn, and it would be the same as any other final drive, and that machine would track straight ahead. Okay, but depending on which way I turn the steering motor, that's going to co-rotate one side and counter-rotate the other side in terms of what the ring gear is doing. And if I speed up one ring gear and slow down the other ring gear, effectively what that does, if I start co-rotating, that's going to slow down the carrier. And if I basically counter rotate on the other side, that's going to speed up the carrier on the other side. And now I sped up one track and slowed down the other, just based on how fast and what direction I was turning the steering motor. That's how differential steering works. Is there more complex, in terms of the way the gears actually work, is there more complex versions of this? Sure there is. But when you really break it down, this is the idea of what we're doing when we talk about differential steering on track type tractors.
A little bit like a high VT transmission, huh?
It's like you're reading my mind, because that's exactly where I was going next with this. Okay, so we talk planetary gears, then we talk about differential steering, and then let's talk about what we got, in the transmission housing of a lot of modern tractors nowadays. It's this exact idea. Okay, it's the notion that if I take a planetary gear and hang on a second here. So if I take a planetary gear set and I have this thing hooked up so that, maybe my engine is going to power the sun gear, right? And perhaps I've got the transmission being driven off of the carrier. And then I go ahead and I hook the ring gear up to a hydrostat drive, like so. And now what I can do is I can use that hydrostat to hold that ring gear stationary. I can use that hydrostat to speed up in terms of co-rotating or counter-rotating that ring gear, right? And if I do it like this, then I can probably end up speeding up the output, slowing down the output. If I ended up counter-rotating the ring gear as fast as the sun gear was turning, then the output would just be stationary, so it's effectively in neutral. Okay. And if I counter-rotate fast enough, I can make this thing drive backwards. And I didn't need any clutches, I didn't need any gears. All I needed was a hydrostat, which would be driven by the engine as well, right? And a simple planetary, right? Now, of course, the mechanical connection is a little more complex than this, but the idea of what's happening is exactly what I have drawn down here. This is how an IVT works, or a CVT. It really depends on whose branding we're talking about here, right? But a continuously variable or infinitely variable transmission. It's basically, when you strip away all the other nonsense, it's a planetary and a hydrostat. Okay. Now, do some manufacturers decide to take this several steps further and add on what's effectively a range transmission to the output? Yeah, they do. Okay, go take a look at Case and some John Deere's. To the best of my knowledge, and I'm pretty sure that Sarah would be able to chip in here, the Fendt ones are pretty much just sticking with what I've got here. They're not all full of gears and clutches and all that other stuff. It's a very, very simple transmission design.
Yeah, that's true.
Yeah. It's not cheap, but it's simple. Okay. So when we're talking CVTs or IVTs, yes, we can go ahead and we can hang a great big gearbox off the back of this if we want to. And then we can start speeding up and slowing down our CVT, which is this portion. And we can play with the ranges over here, which is that portion. Okay. So this is all fine and dandy. Sometimes we don't actually have anything in terms of a CVT. Sometimes what we've got is actually just the range part. Well, I shouldn't necessarily say range, but just the transmission speed. The transmission is the way to change speeds. That transmission, it might be driven directly by the engine, or it might have a torque converter. Either way, we have a way to couple the engine and the transmission together. Transmission drives our drive axle. But what happens inside of the transmission? Typically, in an automatic transmission, we've got a series of wet clutches and brakes. In a power shift transmission, we have a series of wet clutches and brakes, and then some gears. And then just depending on which clutches we apply and which brakes we apply, we can create various different speeds. Okay. If we couple the right set together, we can end up with forward or reverse for our drive direction. And when it comes to an automatic transmission, we used to call an automatic transmission automatic because the valve body that it had in it was able to automatically select the gears for you. Okay. And when we're talking about an automatic transmission with a mechanical valve body on it, that mechanical valve body, it required a governor. Now, the job of that governor was to basically change the pressure value depending on how fast it was spinning. Okay, it was a simple mechanical governor that would act on a spring, that would move a spool, that would effectively change oil pressure. And that varying oil pressure was the signal to the transmission valve body that it was time to shift into another gear. All right. So we would have the governor, which basically is measuring output shaft speed. And then we would also have another input from the engine, which would be a signal related to engine load, a spare modulator, whether it be a vacuum or a direct cable linkage, but there would have been a modulator there. And the purpose of the modulator is to help signal the transmission about engine load. So let's say, for instance, we want to have a very abrupt shift because we've got the engine at higher RPMs and we've got higher power output. So we don't want a real soft, pushy shift. The modulator is going to help to make sure that we're able to get into those higher gears, it's going to make sure that we're able to hold lower gears, and it's going to help us to control our shift. I shouldn't say the modulator controls the shift directly, because shift modulation is also, there's another thing that helps control that. Okay, but if we are talking just simple old school mechanical valve bodies and automatic transmissions, the governor and the modulator, and then of course, there'd be orifices and there'd be what are effectively little accumulators inside of this valve body. They all help to work together to control the shift. All right. Nowadays, that's not the case. If you've got a simple mechanical power shift, we're going to take away, and we're going to start with a simple mechanical power shift and work our way up from there. We take away the governor, okay? We take away any of, call it modulation. This transmission, it's still the same thing. It's still a series of wet clutches, brakes, and gears. And then all you do is you hook a lever up, and that lever lets you position a shift spool to select whichever gear you actually want. That's a power shift. So you are the one who's in control of which gear we're connecting to get power from the engine to the axle. So when it comes to a power shift, is shift modulation still a possibility? Yes and no. I mean, you can control how crisp or how soft the shifts are going to be based on things like an orifice size that the oil can flow through to get to the clutches, right? You can have what are effectively little accumulators that allow that pressure to build a little bit more gradually. Okay, so in terms of shift modulation, can we still do something with simple mechanical power shift? Sure, we can. Right? And it's quite interesting if you think about a simple mechanical power shift. Some of the earliest ones out there, when they're not working properly, you really know it. Has anybody here ever driven an old, say, 3-speed power shift 970? Old case? Okay, I'm going way far back here. Some of those old power shifts, if the shift modulation portion of it wasn't working properly, they're near lift the front wheels off the ground when you made a shift. Right? So it's very important. But nowadays, thanks to electronics, we can strip all of this away, and we can have a valve body that just has a bunch of solenoids that let us select our various different clutches and brakes that we want, and therefore output speeds. Okay. If you took a look at an earlier version of an electronic power shift or an auto shifted transmission, you would have seen a great big valve body hanging off the side of the transmission. And what did you see on there? Tons and tons and tons of solenoids, right? I'm not to say we don't still do that, but yeah, it's just solenoids, and all it is a computer. I won't call this one an ECM, will be nice. I'll call that one a powertrain control module, okay, or TCM. So anywho, this module here would basically be looking at various different things. It might be looking at output shaft speed. Engine RPM. Okay. Shift selector. Throttle position. And this is just a handful of the inputs that we're going to be looking at and monitoring to figure out what gear should we be in, how crisp or how soft should I make the shifts, right? And we take all of this, we feed it into a computer, and we let the computer decide which gear we want, and we call that an auto shift. Okay? Now, a lot of the auto shifts will give you manual mode where you can select your own gear anyways, right? So nowadays, what I just described here, you might call it an automatic transmission if you've got a torque converter in front of it. You might call this type of transmission an auto shift. You might call this a power shift if you still make the operator manually select the gears and not just the direction. Okay. But you strip away whatever the control mode is and you take a look at it, the transmission itself is the exact same thing, isn't it? Gears, clutches, brakes, controlled by a hydraulic valve, or valve body, I should say. And this is what we've got. Now, when it comes to troubleshooting a transmission like this, what do I have up on the screen here? Does this look familiar to anybody? We got a couple nodding. So this is a clutch application chart. A clutch application chart and power shift, automatic, auto shift, call it whatever you want. A clutch application chart is one of those things that can be really useful when you're trying to figure out what exactly is wrong with a transmission. Okay. So if you've got a transmission, then you've got the series. In here we've got clutches and we've got brakes notified, or those are denoted by the C and the B there. But I do want you to focus on the fact that for certain particular speeds, you've got the same clutch being used. All right. And then for other speeds, that clutch isn't used at all, or that brake isn't used. So what you could do with a clutch application chart is you could go through and you could pressure test your elements, shift through every single gear, and take a look and see if we've got a pressure drop. Or we could go ahead and take a look at this chart and say, you know what, every time I'm in, and let me screenshot this so that I can draw on it. There we go. So let's say that you're driving, you see that anytime I'm in fourth reverse, second reverse, second, 6, 7, 10, and 11. Okay, so anytime that I'm in any one of those gears, I notice that my transmission pressure goes a little wonky. Come back to my clutch application chart, take a peek here and say, you know what, that's the thing that is common in all of those. So that means when I start tearing that thing apart, I'm going to target brake number 2. When I've got a auto shift or power shift or automatic transmission, I've probably got a hydraulic pump inside the transmission. It's my transmission charge pump, right? That pump is being used to send oil to the shift valve. And it may also be sending oil to a couple of other places. But let's just say that this pump here is going to send oil to relief valve. Let's go with that first. Okay. And to our shifting valve. So what we're doing with this relief valve is we're using it as a pressure regulator. And what we're doing is we're just holding pressure in the transmission. And I'm going to throw a number up here. I'm going to say 300 psi. Okay. So 300 psi, that's your maximum possible clutch pressure. Okay. Lots are going to be lower than that. Some might be higher than that. I'm just throwing a number up here right now. Okay. So 300 psi, that's our clutch pressure. That's what we want to be able to have for it. And then I've also got some other stuff. I don't know, maybe this is an automatic, right? So maybe I'm going to send some oil off to a torque converter, pressurize that torque converter. And if it wasn't an automatic, I wouldn't really need that. Oh yeah, I'm going to go ahead and I'm just going to stick yet another relief valve in here to make sure that I'm holding back enough pressure for the torque converter. And then I've got this leftover oil. Does anybody have any ideas what I might do with that leftover oil? But just dump it right back into the housing, or I'm going to make use of that somehow.
Send it to a cooler.
Probably. I might send some to a cooler. Yeah, I might. If I'm going to send anything,
Might send it through your lube circuit.
that's what I'm thinking of. It's probably primarily going to be the lube circuit there, right? So basically, I'm making use of all the oil that the transmission has. Now, when I get down into the shift valve here, right, I've got all of the different clutches and stuff coming off that shift valve. And if I want to test this transmission out, I could go and I could get gauges. Now, I'm only drawing 4 here, but you can see how many gauges I have pretty quickly, right? I get a separate gauge on each one of those clutch circuits, brake circuits, couldn't I? Or I could put 1 gauge in the lube circuit. How could 1 gauge in the lube circuit help tell me if I have leaking clutches?
Lube pressure is going to drop off more than, say, 5 pounds when you shift into that element.
Correct. So there are certain, troubleshooting procedures that do direct you to measure individual elements, whether it be a clutch or a brake. But there's other service procedures that direct you to measure the lube pressure and then go ahead and shift through all the gears and use the lube pressure as an indication of excessive clutch or brake leakage. Because if I got too much oil leaking past, and it really doesn't matter exactly what the issue is. Maybe it's, a manifold seal, maybe it's a leaking O-ring, maybe it's a leaking gasket between the shift body and the transmission. Maybe it is a piston seal leak in that element, right? But the thing is, it's going to take more of the oil flow. And remember, lube, that was leftover oil. So if there's less flow in the lube circuit, that means the pressure in the lube circuit is going to go down as well. So this is a really handy shortcut to figure out if you have excessive leakage. Instead of going and getting a gigantic bucket of gauges and start hooking it up to every single, that might not even be practical on certain transmissions. But trying to hook it up to every single clutch or brake element, you just throw 1 in the lube, take a look and see what it does. And then get your clutch application chart out and see exactly which ones have the drop. And now you know which clutch or brake you've got an issue with. Okay. Now, I'm hoping that this sounds kind of familiar and you're able to relate to this in terms of something that you might do at work if you're troubleshooting power shift and auto shift automatic. Because at the end of the day, this right here, this is something that is completely relevant to any one of those types of transmissions.